this one is assessment problem 4.6 from the textbook, and it asks us to solve for the voltage V1, which is the voltage across this 24 ohm resistor. So in order to approach this using the node voltage method, I need to choose a reference node, and in particular I'm going to choose the node at the bottom here, and then I will label the node V1 to be the one directly above the resistor, in order that my node voltage V1 is equal to the V1 that the question asked me to solve. Therefore, I should label V2 and V3 as the other nodes on my circuit. Now, when you look at this, you might initially think that you actually want to do a supernode, where you have all of this area that I've drawn around in purple as a supernode. And the reason why you might think that is that you have two nodes which are connected by a voltage source. But if I actually look a little bit further at this circuit, I will also notice that there's the 60 volt source over here. And so that means that I can't easily write down an expression for the current that's flowing through that 60 volt source. So the current here is not easy to write. So doing KCL at this supernode is not going to be kind of mathematically easy to write down. So therefore, I should not use a supernode to analyze this. What I should do instead is I should actually recognize that the voltage V2 is already specified. I don't even need to calculate it. I can just look at the circuit and read off straight away that V2 is equal to 60 volts, because that source will always ensure that that's the case. Then I can look further at this circuit, and I can recognize that the voltage source on the top branch here, that this voltage source will in turn tell me information about V2. So in particular, it will tell me about V3. So it will tell me that V3 minus V2 is equal to 6 times I phi. So by the way, this symbol here, with sort of the circle with the line through it, this is a Greek letter phi, in case you haven't seen it before. So just looking at this voltage source tells me V2 minus V3 is 6 times I phi. And of course, I phi I can read straight from the circuit using Ohm's law. So I phi is simply V3 minus V1 divided by 3 ohms, right? That's just using Ohm's law here on this particular branch. So this already gives us quite a lot of information about our circuit. So I'm just going to tidy up what we already know, and then I'll go ahead and apply KCL at really the only other node that we haven't already properly analyzed, and that's V1. So first, let's clean up what we have written here on the right-hand side. So I'm going to substitute what I know about I phi into my expression for the voltages. And so this will give me V3 minus V2 is equal to 6 times V3 minus V1 divided by 3, which can simplify to give me 2 V3 minus 2 V1. Now V2 I already know the value of, right? V2 is 60 volts, so I can substitute into this equation, and I can also algebraically simplify it. I can collect some like terms. So if I do that, I will end up with bringing V3 to the other side. I will have my value for V2 will be 60. I'll be left with just factor of 1 in front of V3 minus 2 times V1. Therefore, V3 is equal to 2V1 minus 60. All right, so let's keep that as a first piece of information. So I'm going to call this one here equation number 1. The next thing that I'll do to analyze this circuit is write Kirchhoff's current law, write KCL at the node labeled as V1. And so when I do that, here's the equation that I'll get. So the currents leaving along the left branch is V1 minus V2 divided by 2 ohms. The current leaving on that downward branch is simply V1 divided by 24. And the current leaving on the rightward branch is V1 minus V3 divided by 3 ohms. And all of those currents must sum to 0. So at this point, we can simplify this a little bit. So I'm going to multiply both sides by 24. I just want to eliminate some of these fractions. So if I do that, I will end up with 12 times V1 minus V2 times, so 24 will cancel with the 24. That will leave me with plus V1 here. And then 24 divided 3 is 8, so this will give me 8 V1 minus V3. 24 times 0 will be 0. I can simplify this one a little bit, collect some like terms. So I will have for V1s, I will have 12 and an 8 is 20, plus 1 is 21. So 21 V1. For V2, I will simply have minus 12 V2, and for V3, I will have minus 8 V3 is equal to 0. Now I can substitute in what I know about V2 and V3. So substitute for V2 and V3. V2 was plain old 60 volts, and V3 we have equation 1. So let's go ahead and do that. So this will give me 21 V1 minus 12 times V2 was 60 volts, minus 8 times V3 I've just solved for is equation 1, so that's 2V1 minus 60 is equal to 0. At this point, I have one equation, one unknown, and it's the voltage that the question's asking me to solve for, so now it's just a matter of solving these equations. So let's just go ahead and do that. So I will simplify and expand the brackets. And so here I will have 720, and then that would be minus 16 V1 plus 480 is equal to 0. The V1 terms here will leave me with 5 V1, and I will just calculate what I will get for these numbers. So that's negative 720 plus 480 is minus 240. So V1 is 240 divided by 5, which is 48 volts. So in summary, to analyze a problem like this one is actually easier than it looks at first sight, and the reason is we recognize that this voltage V2 is constrained by the voltage source, and then again this voltage V3 is further constrained by this voltage source, so we can write down quite simple expressions for what these voltages are. And so then there's really only one remaining node where we have to use sort of the traditional Kirchhoff's current law to generate an equation that describes its dynamics. So it's an important pattern that you recognize when you see voltage sources that connect particularly from the reference node to a node, but also whenever you have voltage sources connecting nodes together, you don't have to use a supernode type approach. You can also just write down what is the difference in voltage generated by that voltage source. And that can also be a useful way of solving these sorts of problems.